So my article aimed at giving a brief introduction to breast cancer stem cells and stem cell pathology, to hopefully give an introduction to both a scientific and non-scientific audience, enough foundation on these topics so that I can introduce my personal research project and describe its implications in cancer research thus far. So I think I'll give a summary of my article in a similar manner. So to start off, breast cancer is a major cause of cancer-related deaths amongst women in North America. It causes over 5,000 fatalities in Canada and 40,000 in the US annually. And although these results sound staggering, they actually represent less than half of the total cases of breast cancer that occur. And this is because of recent advances made and breakthroughs made in cancer research that allow oncologists and doctors to make and improve chemotherapeutic strategies and regimens and improve patient prognosis. But at the same time, 30% of breast cancer patients treated for early stage disease with conventional chemotherapies and endocrine therapies still relapse and experience recurrence. So without going too much into the epidemiology about breast cancer, I just wanted to show that these statistics show that it's a very complex and multifactorial condition. And this is because primary tumors have such diverse heterogeneity and they have such a discrete array of gene expression profiles and cell morphologies. So investigators are trying to categorize and classify these different subsets of breast cancer so that targeted specific therapies can be made for more or less metastatic breast cancer, for example. So nevertheless, in the past decade, a small subset or a minority of cells, termed breast cancer stem cells, or tumor-initiating cells, has been identified. They've been functionally classified. And the leading hypothesis now is that these cells are responsible for driving tumor metastasis and are responsible for the recurrence that occurs in tumors following remission of the initial tumor. Now, I mentioned in my article that normal human stem cells play vital regenerative roles in our bodies, and this is true. Normal stem cells play essential roles ranging from embryonic development to organogenesis, tissue regeneration, and even wound healing. And the key to their potential lies in their capacity for unlimited self-renewal and multilineage differentiation into any of the types of cells in the tumor or the tissue. So the problem arises when these cells turn malignant by aberrations caused by an accumulation of genetic mutations that occur due to chemical mutagens or radiation or even viral infection. And when this happens, this population of cells retains the stem cell-like characteristics, but now they have a dysregulated cell cycle function. And they also retain the ability to resist chemotherapies and radiotherapies. So this is where the cancer stem cell hypothesis predicts that this minority population of cells is capable of unlimited self-propagation of the cancer, but also gives rise to a population of phenotypically diverse but non-tumorigenic differentiated cells that make up the bulk of the tumor. And this is what we find in human and mouse tumors. So this prediction is evidenced by studies with non-obese, diabetic, severe combined immunodeficient mice, where they're transplanted with less than 100 putative breast cancer stem cells, and they're able to develop tumors. But whenever these cells are serially passaged into subsequent mice, the tumor still develops, but also gives rise to this population of differentiated tumor cells. These tumor cells make up the bulk of the tumor. We see this in human models as well. But when these cells are transplanted into the mice, they don't develop a tumor unless literally millions of cells are transplanted. So the successful elimination of a cancer requires anti-cancer therapy that affects this differentiated tumor population, but also this potential cancer stem cell population. So at present, current anti-cancer therapies involve chemotherapy, radiotherapy, immunotherapy, and hormonal ablations that affect the rapidly growing differentiated cells that fall victim to these traditional therapies, but that select for or potentially behind this population of cancer stem cells. So even having this model at hand doesn't make it easy to find anti-breast cancer stem cell therapies. Being able to do this requires an in-depth knowledge of the intracellular and intracellular signaling pathways that govern self-renewal and the microenvironmental cues that promote self-renewal and tissue differentiation. So amongst such signaling cascades include the Wnt beta-catenin pathway, human epidermal growth factor, and sonic hedgehog, which I've mentioned in my article. But amongst these is the Notch pathway, which I've decided to focus on. And this pathway has been known to be highly involved in normal mammary development, self-renewal, and cell-fate decisions. But at the same time, it has also been implicated in maintaining the cancer stem cell phenotype and drug resistance, primarily in breast cancer. So a quick literature review will show that Notch signaling is just so central to breast cancer. And this is because you'll find that it interacts with these other developmental pathways in extensive ways, in complex ways that aren't known yet. But you can find in a quick literature review that it has many connections to all these other pathways. And discovering these complexities will give a great insight into how we can tackle, targeting these breast cancer stem cells. So my project aims at validating and identifying small molecules that can inhibit this signaling pathway. But unlike the conventional approach to Notch inhibition, which has involved the use of gamma secretase inhibitors, I plan on finding small molecules that target the intracellular Notch domain that specifically interacts with other transcription factors that exert transcriptional control on oncogenic genes. And I've described the pathway in my article. But what the utility of this approach is that it will allow specific inhibition of Notch while minimizing unwanted side effects. So the way the assay has been designed to assess or identify molecules with this ability, I know I've mentioned the details in my article, but essentially I've used breast cancer cell lines that have incorporated Brunella and Firefly luciferase reporter assays, luminescence assays. But what's interesting is that following a large screen of compounds on one of these cell lines, is that a drug named selenomycin was found to have the most significant and reproducible inhibition of Notch signaling, at least based on the way I've been assessing inhibition of Notch signaling in my assay. But as I mentioned in my article, a few years ago, selenomycin was discovered as an anti-breast cancer stem cell agent. So this result is very promising, and I don't think it was coincidental. I think it shows the large role that Notch plays in breast cancer stem cell maintenance, and it also at least maybe not validates, but fails to invalidate my assay as a means of, or as a tool for identifying compounds that are both Notch and breast cancer stem cell antagonists. So I think it's rather unlikely, given the uniqueness of each breast cancer patient's malignancy in terms of severity and prognosis, tumor grade, and just the overall characteristic heterogeneity associated with primary tumors, that we're going to find, that elusive magic bullet that is the be-all, end-all to breast cancer treatment. But given this, I decided to focus my article on Notch signaling and breast cancer stem cells to first outline the importance of having a breast cancer stem cell directed treatment strategy. And the second thing I wanted to point out was how crucial it is to have an understanding of stem cell physiology. and understanding the complex interactions that occur that mediate self-renewal and tissue differentiation, and how they sustain this breast cancer population. But more specifically, I guess, I wanted to convey the contrast between the conventional means of inhibiting Notch and my particular approach to inhibiting Notch. And the conventional way, as I mentioned earlier, is by using gamma secretase inhibitors. And I mentioned this, the way this enzyme works in my article, but essentially the gamma secretase enzyme allows the Notch receptor to be cleaved at the membrane, and it causes the intracellular Notch domain, which is the active part of the Notch receptor, to enter the nucleus and exert transcriptional control on oncogenic genes. But what I plan on doing is targeting this intracellular domain specifically, or rather the protein-protein interactions that allow it to create a transcriptional activating complex. And other ways that Notch has been tried to be targeted is by using Notch receptor and ligand monoclonal antibodies. And these preclinical models have done very well, especially gamma secretase inhibitors. They themselves are even in clinical trials as of right now. But there's major setbacks to both of these approaches. And an approach that targets Notch in the way that I plan has not been done yet, using small molecules anyways in both preclinical or clinical trials. And I think that finding a small molecule that can accomplish this will do well in a clinical setting and as a form of adjuvant therapy for patients. I think the general takeaway message from my article is that uncovering the complexities and dynamics of breast cancer stem cell physiology will provide the clues needed to develop effective therapies against it. And it will allow us to establish specific targeted therapies on a patient-by-patient basis. And I think that is the way that the battle against breast cancer is going to be won, by targeting or treating patients' specific malignancies rather than breast cancer in general, and by individualizing medicine. As our knowledge of stem cell biology increases every day, we can better optimize the formula for creating chemotherapeutic regimes for patients and to better their prognosis. And in this manner, with this knowledge about stem cell physiology, we can forfeit chemotherapy administrations to patients who we know have a very high prognosis, and this will relieve them from the acutely toxic side effects of many chemotherapies. But perhaps more importantly, it will just relieve them of the emotional burden that chemotherapy has on these patients. At the same time, this knowledge will allow us to recognize poor prognosis patients, and recognize that their malignancies need to be treated immediately and aggressively to prevent recurrence. So my research involving stem cell signaling cascades and stem cell regulation can be extended to a wide range of clinical applications. And this is because these fields are rapidly evolving fields, especially in the last decade. And they have enormous implications with regards to disease-free and recurrence-free survival and regenerative medicine. Notch signaling has been implicated not just in breast cancer, but in cancers of the brain, the pancreas, and several other hematopoietic and immunological malignancies. This is because Notch is amongst one of the handful of signaling pathways, of ancient cell fate signaling pathways, that is conserved in practically every organism, and is implicated in tissues throughout our bodies for development. So understanding how Notch and similar signaling pathways create a signaling network that regulates self-renewal and tissue differentiation will provide a massive leap in cancer therapy. It will be easier to identify small molecules that can target a specific molecular target that we know needs to be targeted. And this kind of drug therapy also brings with it the ease of administration, oral bioavailability, and low cost, which antibody cancer antibody therapy doesn't provide right now. Our research can even have implications in regenerative medicine and in developing a model towards the origins of cancer tumor development. So the 2012 Nobel Prize in Physiology and Medicine was awarded for the discovery that mature differentiated cells can actually be reprogrammed into a pluripotent stem cell state. So in breast cancer, this kind of de-evolving back into a pluripotent state is called epithelial to mesenchymal transition, or EMT. And it has actually been known to be associated with activated mutations in Notch. So you can see how understanding the factors and mechanisms of Notch-mediated tissue differentiation can help establish a model for the origins of cancer, but also aid in generating stable stem cell pools for regenerative medicine, because right now it's very hard not only to get funding for embryonic stem cell research, but it's very hard to obtain stem cells. There's a shortage of them.